It's indeed time to start again. It's 2 o'clock. Also, the people in the live event will join again probably. We now have 37, I see. So there should be some more. Well, we had almost 60 this morning. This afternoon we have two presentations, one by Oguzhan Copuroglu and one by Paola Antonacci. She will join later. And Oguzhan is assistant professor at Delft University, and he's an expert in durability, concrete materials, cell feeling also, but among everything, he's a specialist in microscopy. And that's what he will talk about this afternoon. What you can do with microscopes also to study materials and cell healing, how you can make use of them. So Oguzhan, I will give you the floor. If you,
Thank you very much. Hi everyone. Well, it was a nice introduction, so I have nothing to add, of course. Just let me just do the test in the beginning. Is my voice clear and loud and everything? No problem, right? I see thumbs up. That's perfect. So yeah, well, I see that this is a training school. I don't know the very details of SmartThings, but I can imagine that there are many people here who would like to learn a little bit about microscopy. And if you know the microscopy, that's great. It will be just a refreshment for you. But if not, perhaps I can inspire you, I don't know, with some techniques that you can use in your research towards characterization of self-healing materials. So today, my presentation will be mainly devoted on the cementitious materials, but no problem if you're dealing with any other type of material, because the principles are basically the same. All right. So without losing much time, because I think I have 2 hours.
You have 2 hours, yeah, that's true.
Okay, perhaps with a break in between or not?
Yeah, you can plan yourself whenever you want to break.
If I see heads falling down, then I'll stop. So yeah, let's just start and see where we go. Again, this is a huge topic. I mean, just to give you an idea, we are annually we are teaching concrete microscopy course to PhD students like you guys during a week. I mean, it's a really heavy program, and today what I will try to do is I will try to summarize in a crash course. You'll get the ideas, and if you want to go deeper in those subjects, I think it will serve you well as a kind of guide. So let's not waste time. Let's immediately jump into the presentation. So first I should share, I believe.
Yeah.
My presentation. Is this clear right now? Are you all seeing the front page of my slide?
Yes.
Yeah.
It says microscopy applied to cementitious building materials, but again, cementitious can be metallic, can be polymers, can be this, it just doesn't matter. I mean, microscopy is microscopy. In the first part of my presentation, I'd like to give you more information about optical microscopy and how do we use that? What are the principles of using an optical microscope in our research? And then I will dive into the second part. Hopefully we will have enough time to talk about electron microscopy. So why? Because these are the two main microscopy techniques. That doesn't mean that these are the only ones, not at all. I mean, the technology is evolving and we have new techniques, but I'm quite sure my other colleagues covered some newer techniques like computerized tomography. And so those techniques can also be easily considered as microscopes or microscopic techniques. But today we will only concentrate on the optical and electron. All right, let's get going. So what is actually microscopy from a concrete person point of view? Because, well, may I ask a question to you, Erik, or anybody? What is the background of the audience? I mean, is it generally people who are interested in concrete and will do research on concrete, or is it really mixed?
The people here in the room, they are all working on self-healing. So 15 PhD students working on a project on self-healing, but with different backgrounds. All aspects of
self-healing on concrete or?
Self-healing on concrete, yeah.
Oh, okay. Excellent. Okay.
And all people in the live stream can have any background.
All right. well, then this is the maybe possibility for us to make some advertisement. Great, but at least let me call you the main audience, the smart things people. You are the concrete people, so it is just fine, I think, to concentrate on concrete today. Again, when we talk about microscopy in cementitious materials, typically people like to give a name of for that field, and that is either concrete microscopy or concrete petrography. So what is this? When you think about concrete microscopy, don't immediately think, hey, this is only about microscopy, and if I have a microscope only, I'm a happy camper. I can do my job. No, that's not the case. Actually, when we say concrete microscopy, it means this is a series, like collection of protocols to characterize our material, okay? And so what are we characterizing? Actually, we are characterizing the microstructure of our material in order to make connections with its durability, with its mechanical properties, and general behavior. Wait a second, I lost my screen for whatever reason. So we were talking about the concrete microscopy. Let me get going. It is, again, to characterize the microstructure and to make connections with its behavior. So what can we think of when we think about these protocols like optical microscopy, electron microscopy? Okay, fine, but also there are some complementary techniques like X-ray diffraction, image analysis, and so on and so forth. Of course, today we will not dive into all of them. All I want to say here is that don't think like microscopes are enough for your research only. I mean, you will definitely need some complementary techniques to make your point and have good analysis results. Good. And why people keep on calling it concrete petrography? Because petrography, do we have any Greek students in our audience? Probably not, because I'm not hearing. But if you know Greek, I think it's petrography, as far as I know, it means just a graphical definition, description of rocks. So petro being rock. So because our concrete is a man-made rock, why not? We can use all the principles of petrography science on concrete, and this is the end result. All right, so here are the general fields. In general, when people use microscopy on concrete or cementitious materials, we generally divide into two, being the concrete microscopy and cement microscopy. When you look at the concrete microscopy, you can do tons of things, starting from mixed design verification, analysis of constituents, like diagnosis of durability related issues. Some of them I will touch upon today. But you see, there are many things you can do to characterize your concrete and have an idea about its expected durability. Cement microscopy, on the other hand, is a little different. It is mainly used at the cement manufacturing facilities, cement factories. Why? To be able to get an idea about their production quickly, instead of waiting long periods of times to see if your production is indeed a SAM 1, 32.5, 52.5 or whatever. You can analyze the clinker components to have an idea about its strength development, early age strength, and so on and so forth. So it's specialized microscopy technique, certainly possible to understand and study. Perhaps some of you will be interested later on. This is just to let you know that it exists and it is very much related to our business. All right. If you want to do microscopy, of course, we need specimens, right? Anything is possible. You can use anything, but it's always best to prepare them according to the technique we are planning to use. In general, we divide our specimens into two. Generally, we have thin sections and polished sections. Thin sections are generally used for optical microscopy, and if you polish it, you can use it for optical microscopes and also the electron microscope. You can imagine why we're making it super thin, because it is needed. We need our light to pass through this thin section and come to our eyes or detectors, which are called the microscope camera, right? So it's some sort of eye. So when you have thin section, that doesn't mean that you cannot use it with electron microscope. Of course, if you don't put a cover glass on top of it, but just polish it. You can use it for under optical microscope and electron microscope. So there is actually no difference once you polish. So possibilities are endless, but basically just to divide into two categories, these are the two different types. So how we make thin sections after cutting, we gradually grind down to about 30 micrometers. I don't know, you all can see me, right? So a thin section would look something like this, I mean, in size. And the thickness of a thin section is about 30 micrometers, which is about 1/3 of your single hair. Imagine how thin we create out of a piece of rock. And how do we do that? Of course, as you know, concrete is a super brittle material. It is not easy to shape, to grind. That's the reason we prefer using low viscosity epoxy, including a special dye. You see special color inside, which is able to react to ultraviolet light. And we impregnate our porous concrete to make it really robust and strong during all this cutting, chopping, and grinding operation. And finally, again, with these machines, we achieve a 30 micrometer thickness. Polished sectioning is kind of relatively less labor intensive, but it's still very serious business. Again, why do we need it? We need a mirror quality, mirror polishing quality typically for electron microscopes, but also if you have a reflected light microscopy, not transmitted light microscopy. So there are two types. The light can pass through it, or you can send the light from upside down and it can be reflected and you can observe. So these polished sections can be used with reflected light optical microscopes and or electron microscopes. So typically there are two stages you can think of if you want to prepare polished sectioning. So these are called grinding and polishing, but actually they are the same thing. All we do is just scratching our material surface, finer, finer, and even finer. So fine that we will not be able to see those scratches even under the microscope. Then you call it polished. Actually, if you go super deep, then you will see those scratches at a submicron level. But that's of course something we're not interested in. All we want to have is a well-polished surface at the magnifications we're interested in. Okay, and for that reason, we use, for instance, for the first stage, you can use some silicon carbide papers, basically sandpaper, and then in the second part, you can continue with the diamond sprays and diamond pastes to further grind it all the way down to 1/4 micrometer, as you see. So the end result is, I have something like that here. So this is a really large polished slab. I don't know if you can see the reflection. Does it make any sense that I'm doing this? Can you see me? Because I'm not seeing you.
Yes.
Yes. Okay.
Yeah, looks good.
All right. If you see the reflection, this is the quality we're trying to achieve. All right. But so we were talking about the microscopy in general, and loosely, globally, we're dividing into two: optical and electron microscopy. The optical microscope side, we will now talk about it, of course. And electron uses very similar principles. The only difference, the main difference, is the source of imaging, source of light. In the left-hand side, on the left-hand side for optical microscopes, we are using light, visible light, and for electrons, we use another electromagnetic emission, which is the electron. You see next to it an X-ray. That is not a microscope, of course, but it is, and it can be used for imaging purposes as well as for chemical characterization. And it is a kind of attachment, or it is the part of a modern electron microscope. So we cannot think it as a different thing. Unfortunately, we will not have time to dive into the X-ray microanalysis today. Perhaps another time we will have that opportunity, but today we will only look at these two optical and electron microscopes. So let's start with the optical light microscopy. So again, we are using the visible light waves. Do you know what the visible light is? Can anybody tell me? Do we have Q&A like this, or do you prefer monologues? I don't know what the setting of this course is, but If
No,
somebody
you can
can tell
start
us.
discussions, but that's good.
All right.
Wake them up.
So wake up. What's the visible light? What do you understand by visible light? Too late. It is. I mean, of course, I can wait, but then I will not be able to finish my material. But we are talking about the nanometer scale of wavelength, right? Nanometer level. So from about, I don't know, about 400 nanometers or slightly less, going all the way up to 750 nanometer is the visible light, starting from ultraviolet, going all the way up to infrared. We can observe that, but not beyond and below. But we can still use it in our microscope techniques. But when we talk about optical microscopy, again, generally we divide into two. Number one is a stereo microscope for low-level, low magnification studies in order to have an idea about the overview. And you can also consider compound microscopes for high magnification, high resolution, detailed analysis of phases. For example, the polarized light microscope, that is a typical compound microscope we use in concrete microscopy. So when you think about the stereo microscope, of course, you should just think basically like a loop or a magnifier, a standard magnifier that you would use to, I don't know, to browse your atlas at home, or I don't know, to read your mail or whatever if the letter is too small. So this is just a very high quality magnifier. It gives more three-dimensional sense, and you can see formations on materials like this easily. So you see on the left-hand side there is some sort of popcorn developing on our concrete, right? This is an alkali silica gel. And on the right-hand side, you also see an aggregate cracked and some products developed inside, which also belongs to an alkali silica reaction product. But this is it. I mean, this is the level. But of course, from self-healing point of view, it's a very interesting and very handy tool. You see here from one of our studies, monitoring of the healing of a crack, and at day 0, 3, 7, and 14, you can observe clearly the closing of a crack based on the self-healing technique you adopted. And it's very simple, very quick. It doesn't really need a lot of preparations. That's the reason it's a very, very good tool, and you should definitely have the stereo microscopes in your lab. Okay, but let's look at the compound microscopes, because stereo microscopes, again, you really don't need a lot of information. All you need to do is to be able to focus on the surface of your material, and that's about it. But polarized light microscopy, or the compound microscopy, is a little different. It needs some fundamental knowledge in order to be able to understand what you're seeing and what it means. What all the observations mean under these types of microscopes. So what you can do with these compound microscopes, or POL microscopes in short, that you can use two different light modes, which we very briefly we call them PPL and XPL, like plane polarization and cross polarization. And the names come from the filters we use in these kinds of microscopes. If you use only one filter, you would call the image you're seeing, or you're taking the picture as the PPL mode picture or photomicrograph. And the other one would be called the XPL, or cross-polarized light photomicrograph, what you're seeing right here. So at this moment on the slide, you are seeing exactly the same spot on a material, and you see yet different colors, right? They are completely different. On the left-hand side, you see a more realistic looking surface. Why realistic looking? I'm saying because of the colors. I mean, they look somehow natural colors. And on the other side, you see some different colors, like psychedelic colors even. I mean, this is like unreal. I mean, in real life, if you take a piece of rock, you wouldn't see these colors with your eyes. And that is indeed so. So with plane polarized light mode, we observe the real color of our microstructure, and the cross-polarized light gives us special colors, characteristic colors of those phases we are observing. It can be some crystals perhaps, or glass, or whatever. And these differentiations are based on being transparent or opaque. Transparent means it can transmit light. Opaque means light can come but cannot pass through, so you will see it dark. And then the transparent can be crystalline or amorphous. I mean, these are the really basic classifications of our microstructures. And when later on you will be dealing with self-healing materials, you will observe lots of amorphous phases and crystalline phases, and maybe you will be concentrating on, I don't know, calcite-based self-healing. So that means you will develop a lot of calcite, calcium carbonate, which is crystalline, which is anisotropic. So it will show specific features under this plane polarized light or cross polarized light. And those psychedelic colors I told you, they just depend on the property. I mean, this is just an inherent property of certain crystals, which we call birefringence. This is just a property of certain crystals, and they show specific colors at specific thickness, so that we can know, oh, okay, I mean, if it's quartz, I know that it's at 30 micrometers, it will show this white color. Or if you're looking at, I don't know, calcium hydroxide, you know that at 30 micrometer of thickness, you would get a color something like this. Why am I emphasizing 30 micrometers? Because you remember your thin section is 30 micrometers thick, and there is a reason for it, because we don't want to guess each time what kind of color should I have on this mineral or crystal or phase. In order to avoid this, we try to get a standard thickness, and we then know what kind of color we can expect from our crystalline phases under crossed polarized light imaging. And of course, in order to be able to exercise all these things, you should very well know, or you should have access to the optical properties of main phases in concrete, because you're going to work on concrete, you're going to work on self-healing of concrete. That means you need to know about the phases of concrete, or your cementitious phase, right? The unhydrated phases, hydrated phases, maybe there will be secondary products like carbonation and ettringite. There will be, of course, porosity, voids and cracks, capillary porosities, and aggregates. What kind of aggregate are you using? Quartz-based, carbonate-based? All these things can easily be characterized with this optical microscopy techniques. So let me give you some examples. Here you see a plane polarized light image of a clinker, piece of clinker. Here we can easily identify the A light crystals and B light crystals based on their shape only, because we are seeing their natural colors. A light is typically angular shaped and relatively larger than these rounded grains of B light. How and why is not the topic of this lecture today. It is all, I'm just trying to give you very quickly some possibilities. And if you're interested in diving into details of it, of course, I will be happy to help you with finding your way out. So here you see another example. Again, under the polarized light microscope, you can observe not only very detailed features, but you can also look from far away. And when you do that, there are multiple advantages to it, of course. Then you can see the grain size distribution of your aggregates. You can even do point counting and have quantitative information. You can observe entrapped air. You see all these irregular entrapped air can easily be observed at very low magnifications. You see this upper left-hand side is a low magnification, because you can easily understand by looking at the field of view, which is from left-hand side to right-hand side of this image. It's 11.5 millimeters. It's quite large. But you can change your objectives from 5 to 20 to whatever you have in order to have the details of your microstructure. So that's the beauty of microscopy. Actually, you don't need to only look at a single magnification, but you can zoom in and zoom out and go to different spots to understand your material even better. So we were talking about this transparent and opaque features. So here's one example. This here you see an opaque, rounded shaped, while here you see transparent features. You see, when I say transparent, many people think that, oh, it should look like glass or maybe white, okay, but this is not transparent. No, this is also transparent up to a certain point. I mean, it allows light to pass through so that I can see its features, right? I can then say, hey, this looks darker, I don't know, it's wavy, and so on and so forth. If it is completely pitch black under transmitted light microscopy, then you would call it opaque. That means the light cannot pass through. Can you think of any example, for instance, in concrete, what kind of phases would be opaque? Light cannot pass through. So this one is most probably a steel fiber. Just by chance, it was cut through this steel fiber. So the light, when I sent from down to up, it cannot pass through. So I see it in an opaque form. Some more examples. You are here observing a crack, for instance, filled with a lot of secondary products. And you see in plain polarized light, you remember I was seeing the natural colors. And all these white deposits here, they are all alkali silica reaction gel, or maybe up to a certain degree, some crystals are also here. So how can I understand, or how can I say, hey, is this a gel? Is this really glassy alkali silica reaction product? The only way to see is to identify it if it is an amorphous structure or if it's a crystalline structure, because I know that ASR gel is a glassy microstructure, so it should give me isotropic features. And the only way, again, is to do this by testing optically, by going to the crossed polarized light mode in my microscope, by just inserting that secondary polarizing filter, and then I see everything super dark, you see? So if this is completely dark, it tells me that this is not a crystalline deposit, it is an amorphous deposit, which lets me tick one more box to identify it as an ASR gel. And on the other hand, if you look at this aggregate, which is next to this crack, you see that it is formed by tiny grains of crystals. I can tell you these are quartz crystals. How do I know that these are crystals and not gel or amorphous materials, amorphous phases? Because I can observe some colors in the cross-polarized light imaging mode. Because that's the only reason, that's the only way I can tell that these are crystals. If they weren't crystals, they would have been observed like this, super dark. So again, long story short, if we observe certain colors in cross-polarized mode, we can say that they are anisotropic, they are crystalline phases. And again, in your research, you will deal with a lot of different crystals, like calcite comes to mind very quickly when you talk about self-healing of concrete. Again, you might be interested in observing your binder, because please note that these microscopy in general is not only used for research and development, but also for forensic engineering, which means to identify and characterize the material when there's a dispute. There can be, so that in a project, people can approach you and say, we have here a concrete, but we are in dispute with the contractor. I'm the owner. I think that they should have used SEM1 because it's written in the contract, but they used, I think, something else. Could you check and let me know if this is indeed a SEM1 binder or SEM3 or SEM2 or whatever? So for these kinds of questions, concrete microscopy, concrete petrography, again, is a very, very useful tool. So one example here, if you're interested in finding out if you have ordinary Portland cement, of course, what you need to look for is a lot of unhydrated cement grains full of B light and A light. And here one example, perhaps you can find the spot between your aggregate particles. That means your binder. You can zoom in gradually to observe all these A light grains and B light clusters typically. This is, again, just one example. Here you see really large clusters of B light grains partying. They are super social crystals. You always observe them together. like this, especially if the concrete is quite old. The newer concretes, cements produce with smaller clusters, but the older cement production shows typically these kinds of large B-like clusters. Again, some even further magnification. You can not only ordinary Portland cement, of course, you can also observe like other binders such as slag. Slag is quite popular in the Netherlands. We use quite a bit of blast furnace slag cement. You see on the top, here we see the blast furnace slag cement paste. On the left-hand side, you see the plain polarized light. Yeah, natural colors, all the grains are visible, everything's fine. If I go to cross-polarized light, you remember if it's super dark, it would tell me that I have amorphous grains, and all these grains, these white grains you see on the left side, you see them quite dark on the right-hand side because they are all amorphous and they are showing all these isotropic features, which means dark. If you look at the lower side, you might say, okay, I again see something similar there. They are, give or take, similar in shape. Yeah, that is true, but they are not slag grains. Why? Because you should pay attention to the scale. That's all I want to do here, is not to teach you how slag should look like or whatever. That is deeper discussions and everything, but all I want to tell you here, the importance of scale and using scales for micrographs, be it photomicrograph or electron micrograph, you must always use scales. Otherwise, it will be very difficult to evaluate what you're looking at. You see on the bottom side, on the bottom row, you're seeing glass aggregates. They are not slags. They're just aggregates, very large aggregate particles. But in cross-polarized light, again, you see quite dark, give or take similar features. Why? Because they are also amorphous. That's the reason they should show similar characteristics. But the only way I can tell, hey, this is not a slag, but this is a glass particle, is to check my scale. So please, oh please, whenever you're dealing with photomicrographs or micrographs in general, always use scales. Here, another example, differentiating between ordinary Portland cement and slag cement. You see ordinary Portland cement microstructure looks quite bright. There are tons of fireworks going on there, right? I mean, you see a lot of colorful inclusions here and there. But on the right-hand side, the CEM3 slag cement paste is rather dull and boring. You know, it's quite dark. Why? The main reason, if you've been studying cement hydration, of course, because CEM1 develops a lot of calcium hydroxide crystals. And on the contrary, CEM3, especially CEM3B, when you have a lot of slag grains inside, you don't have a lot of calcium hydroxide. That means if I can observe the calcium hydroxide crystals or grains, I can say something about the binder type, right? Qualitatively. And indeed, on the left-hand side, all those colorful stuff belong to my calcium hydroxide crystals. Why are they in such beautiful color? The main reason, again, is because of their physical property called birefringence. All calcium hydroxide crystals at about 30 micrometer thickness will look like this, okay? And because you don't have enough calcium hydroxide in your system, CEM3 microstructure would look like this, super dark and dull. So you can expect this from any blended cement paste. This is another photomicrograph of ordinary Portland cement microstructure with a lot of beautiful calcium hydroxide crystals. Here you see another example of a cracked concrete filled with alkali silica reactions, nothing different here. Again, all I want to emphasize here is that on the left-hand side, you see again the very like simple plain view, and the colors are generally natural. And on the right-hand side, you are observing here an aggregate, and what it helps us to do here is to observe alkali reactive aggregates. We can see super tiny silica grains in our concrete, in our aggregate here, in this aggregate, which tells us that this could be responsible for alkali silica reaction. While the neighboring sand grain is not microcrystalline. You see, probably these kinds of aggregates are not susceptible for alkali silica reaction damage. Just some examples. And here there's another one which is showing a really large field of view. You see it's 3 millimeters. You're looking at the surface of a piece of concrete, and you see it is quite bright, coming all the way down to a certain level, and after that it's all dark. Can anybody tell me why this is the situation here? What's going on here? Why do I have a cement paste here, the binder, super bright, down to a certain level, and then it's going quite dark? Anybody in 1, 2, 3 seconds? I don't see your faces, so what are we looking at here? Any idea? This is the surface again. What could it be? This is again, what do we have in the atmosphere? It is the carbon dioxide, right? So it penetrates in your concrete, and all your uncarbonated, non-carbonated cement paste turns into this bright birefringence in cross-polarized light. Don't forget. Why? Because of the generation of calcium carbonate crystals, probably calcite or other polymorphs. And we observed them in this color because of its birefringence. While if you look at deeper sides of your concrete, you will observe that this you will not have any carbonation evidence. Why? Because you see it dark. Why? Because my calcium silicate hydrate is essentially isotropic, glassy character, let's say. All right. Now this is another view, just summarizing what we've discussed until now. Okay, ettringite is another secondary formation you typically see in concrete as the delayed ettringite formation, secondary ettringite formation, and so on and so forth. You see they are needle-like and can form in any place they can find, basically. You see generally at the interfacial transition zone because you have relatively more capillary porosity there compared to the bulk. But where I'm trying to get at is actually the self-healing, observing self-healing with these techniques. Here you see one example from one of our studies, the self-sealing of a crack opening. So you observe here a crack opening, and we used a certain additive to promote self-healing. But what we observed actually was, instead of self-healing, we achieved the self-sealing. Why? Possibly because higher carbon dioxide content at the surface triggered formation of calcium carbonate. So this is again a plane polarized light image showing all these deposited calcium carbonate crystals here. And here you see the ettringite, the crystals I showed you just now, due to DEF or secondary ettringite formation. You can observe them, but you can also use their formation to your advantage for self-healing. We use the CSA type of additives in our cement paste to see their potential for self-healing, and you can observe that some ettringite crystals have ability to close some cracks, some very tiny cracks up to about 400 micrometers. We managed to heal substantially, but beyond that was quite difficult. But again, with these techniques, you can again observe and identify all these needles of ettringite within your cracks. Here, another one, which is called the active thin section. We use the active thin section to observe the healing mechanisms in time, so not at a given moment, but starting from the beginning. Gradually we wanted to observe, and active thin section means being able to reach the inners of your thin section. So you don't just prepare the thin section, but you also make sure that the cracks are free, accessible, so that you can, from outside, you can send water, you can inject water and try observing crystal deposition, crystal generation in the cracks in this form. So this is a relatively unorthodox technique, so to say, but your keyword to search for is the active thin section. If you have any questions regarding this, later on we can discuss, and I can give you some tips on how to do this. Okay, but so far we've been discussing about the phases, right? The products, crystalline, non-crystalline, so how to understand what we're looking at. But that is not the only thing we're interested in, concrete or cementitious materials, but also pore structure is important. And in order to examine the pore structures, we typically use ultraviolet light, so very low wavelength light. The main reason is, if you remember, when we prepared our samples, we used a special dye, special color pigment in our epoxy. When we impregnate, it's hardened my concrete, it made it really strong, but also it gave a new feature, new property, and that is all the pores and cracks are now filled in with my epoxy with a special color. And that color I can observe by shining ultraviolet light, and then it will release a special green color, which I can observe and take picture and even do the image analysis to quantify the amount. So what can I do? Of course, I can examine entrained air, I can examine entrapped air, I can examine capillary pores. So like this, in really low magnification, you can easily see those entrapped air. You see, these are all because of poor compaction, extreme vibration, you name it. I mean, this is a kind of destabilized microstructure. If you do excessive compaction, then you of course can see these kinds of microstructure. And if you do poor compaction, of course, you can also get a lot of entrapped air. On the other hand, sometimes we want air in our concrete, and we call them air entraining. So we use air entraining agents, special chemicals, to drive all these tiny spherical air voids in our concrete, so that you see they are super small compared to entrapped air, but also well dispersed. The whole idea here is to improve the durability of our concrete when the frost kicks in and the ice front achieves these reaches these air voids. So the water inside my capillary pores can escape to an escape vessel. And that's the whole idea, so that the hydraulic pressure will be released. That's the reason amount of these air voids and their positioning, their spacing, as they say, is extremely important. And with microscopy, you can very well characterize and understand that if your concrete is, let's say, frost immune or not. You can do further things with UV lights. Applications. You can observe cracks, increase in capillary pores. Here you see just half core, polished half core, to examine the cracked microstructure. You can also observe capillary pores, but of course, optical microscopy is known to have relatively low magnification, low resolution. So it's really hard for us to observe pores smaller than 10 micrometers. And that's the reason we cannot see those super tiny capillary pores individually, but we can see their effect. So how much green light we are seeing. If you see a lot of green light coming out of our cement paste, then that we can say, hey, we have high capillary porosity. And if it's very dark, you can assume that it's a low capillary porosity. And by correlating the amount of green light you're observing to some other properties, such as water-cement ratio, you can easily estimate for instance, the unknown water-cement ratio of an unknown concrete. So you observe here the effect of capillary pores under the UV light microscopy, fluorescence light microscopy. It's a more proper term. You see the lower the water-cement ratio, of course, the lower the capillary porosity. That's the reason you see darker microstructure. And as you increase the water-cement ratio, you increase the amount of capillary pores, and you can observe again under the microscope. And please note that when we took these images, all the light conditions were same. So we did not change the light intensity on our microscope. You keep the microscope light conditions same, but when you observe these different water cement ratio microstructures, you will of course see different intensities. And if you kind of correlate them, you will see that there is a very linear relationship between water cement ratio and the amount of capillary pores. I think I'm amazingly on time for the first part. Am I right, Eric?
Yes, you are. It's 45 minutes. So
yeah, I think I will dive into the second part, but I don't know how many sleepers we have. I can't observe. So let me go back.
Here we are.
Here we are. I don't see any sleepers so far. But
oh, they're still there.
Yeah, they're still there. So I will just take a sip. And before we dive into the second part, the electron microscopy, let me ask you if you have questions, because I mean we can of course get at the end as well, but maybe we won't have time. So let's use this this kind of break for very quick Q&A. Are there any questions? Is there something? Because I admit that I'm kind of flying because I have to. There are so many topics, and I just want, my aim here is to give you kind of inspiration, and that's about it. I mean, if you say, hey, oh, this is possible, oh, that is interesting, that's, I think, already a success if we can do something like that. Any questions?
Hi, professors. Can I ask a question about polishing?
Polishing, of course.
Yeah, I mean, when we doing polishing with mortar or concrete, because different phase has different hardness, it's always very hard to achieve a homogeneous degree of the polishing. And especially the cement paste is always very rough, and it makes it very hard for the imaging. So how can we solve this?
Well, let me ask, what is your problem with your polishing? And why are you not happy with your polishing? Yes, it is hard, we know, but
yeah.
But what makes you think that your quality is not good?
Because under the microscope we can see the aggregate has been reflected, but not the paste. The paste is still very rough.
Yeah, but are you using reflected light microscopy?
Yeah, reflective.
And the question is why?
It's not why. It's like how can I also polish the paste part also very good?
Look, you can. Of course, there are multiple things, and there is no formula for that. Let me tell this right away, because we have been polishing samples like, I don't know, maybe last 20 years or so in our lab, and we still do not have a one recipe for you.
Okay.
So what you need to do, there are two options. If you have a manual system, all you need to do is to try to find a good practice for yourself, because if your friend says, I'm doing it like this and that might not work for you. There are multiple reasons for that, because if you're not using your polishing material the same amount, if you're not applying pressure the same amount, if your durations are different, you will get different results. Okay?
Yeah, so there are too many variables in this.
There are very many variables, extremely. Yeah. If your idea is to, I don't know, do a lot of polishing, really extensive amount of specimen preparation, the best way is to change these parameters, and for each specimen go and take a photo under your stereo microscope. Then you will have some sort of guideline for you. Okay, when I use so much, when I did the polishing so long, these are the qualities I'm getting. So you can visualize this. This is possible. But if you say this is very long way and I don't like it, I just want to take my sample and then just start polishing, it should be good and great. What I typically say as a starting point, it is good that you start with first getting a good cut of your specimen, because I see many students, they don't even start with a good rough sample. Their straight soles are really, they're not straight. You see a lot of blade marks on it. If you have a lot of irregularities, then the problem is you will have a hard time coming to a flat surface. So your first task is to sole your sample really as straight as possible with minimum amount of saw marks on it. Okay, that's number one. Number two, once you have that, you need to bring it down to a flat level, which needs sandpaper polishing, silicon carbide polishing. So typically you would start with 320, and then you can go to, I don't know, 500 or 800, and eventually 1200 is a good number to bring it down to a reasonable flat surface. How long? Again, it depends on your specimen. It depends on microstructure. It depends on your aggregates you're using in your concrete, if it's concrete.
Yeah.
Some concrete aggregate types are very hard compared to, I don't know, limestone, for instance. So, so this is one side. The other side is in some labs, there are automated machines, which means you can install your machine and you can even adjust the load on top of your sample holding. So that's great, of course, because then you can adjust different loads and different durations and different amounts of grinding and polishing chemicals, and that will give you eventually a good, repeatable setup, right? Repeatable recipe. So that's relatively easy to achieve. And again, for the polishing part, as I've shown you, what we typically do, we start with a 9 micrometer. We go to 6, 3, 1, and quarter. You can skip 1 or 2 in between, but that will only prolong the duration of polishing. What else can I advise you? We had very poor results with suspensions. We really had very poor results with polishing suspensions we used. I mean, the end result was quite bad. Instead, we are using diamond pastes, which I think polycrystalline diamond paste, and they are really, really good. I mean, I can give you several examples, including one of your classmates, Priya, had really very good experience with it. I think almost all of our students these days are using the paste, the diamond paste, not the suspension. Just another tip. I don't know if it was useful, but again, long story short, it depends. It depends on your facility, the materials you're using, a lot of things. But just be systematic and follow certain grinding levels.
Okay, thank you.
Any other? If not, then let's continue with the second part, which is the electron microscopy. And I kind of feel like most of you will be using electron microscopy. This is just the statistics in my career that I observe students prefer using electron microscopes more than optical microscopes. I think one of the main reasons is that they think that electron microscope is easy to operate. While it is true up to a certain extent, it is also extremely wrong. Why? Because you guys are now professionals, right? You're the professional researchers, and your results should be state-of-the-art quality. The way you produce your micrographs or your analyses. And if you look for quality in electron microscopy, it is not as easy. It's not just click and shoot and save. There are many different parameters. But today we will focus mainly on basics of it, try to understand what electron microscope is, and try to appreciate if it is going to be useful for our research. So let me go back to my screen. So I need to share again, I guess. There we go. Is it visible?
Yeah.
Yeah. Okay. So,
yeah, it works.
All right. So now we will talk in this second part. We will talk more about the definition, anatomy of electron microscopes for those who are new to this. Let's talk about the advantages and working principle. Electron-solid interaction is everything about electron microscope because we acquire images, we analyze all based on electron-solid interaction. So we will touch upon this. We will talk about detection modes, and unfortunately, we will not be able to talk about X-ray microanalysis because it's an entirely different topic and presentation. Hopefully, later on we can find opportunity for this. But what's the difference? Why do we have a second chapter, and why am I not treating electron microscope together with optical? Because the principles are very similar. But at the same time, there are many different ways of operation in electron microscopes. First of all, the source is different. In optical microscopes, again, we have the visible light so that it gives us these colorful, beautiful images. But in electron microscopes, you see, we don't get any color. It is just black and white, and it's film noir. Why do you think it is like this? Why am I only seeing the grayscale, but not, I don't know, some nice yellow colors of this bee? Any idea? Can anybody tell me? You're not really playing, so it's boring. So I will give the answer. Of course, it is because we cannot observe, right? Because electrons have certain wavelength, but it is far smaller compared to the visible light. That's the reason we cannot see color. Yeah, maybe we can see something. We don't know. I don't know if our receptors can react to it. But even if they do, we will not be able to convert it into color. And the system, that's the reason the system just gives you a kind of translation of electrical signal into the grayscale image like this. And if you look at a modern electron microscope, you typically see a column like this. We will see the anatomy as well, but it's typically there's a column where we generate our electrons and send on top of our specimens. And we have a really large chamber in which we can put our specimen and even do certain tests, certain mechanical tests, depending on the size of the chamber. And we have several detectors, depending on what we are interested in. So if you compare with the electron microscope, if you compare electron microscope with the light microscope, there are some differences. Typically, resolution is the most important difference. If you compare with the optical microscope, you can go really, really high in magnification with electron microscopes, down to 5 nanometer with really good systems. But with light microscopes, theoretically, you can have 200 nanometers of resolution. This is theoretical. I mean, in practice, because of vibrations and other reasons, you will probably get far lower resolution. Depth of field is another problem with optical microscopes. If you're interested in photography, you probably know the concept called bokeh. If you take a portrait of somebody with a good lens, you will see that the background is separated in a blurry fashion. That is typically an optical feature that is it is hard to avoid for optics, especially at high magnifications. But with electron microscopes, that's not the case. You can easily have deeper 3D-like appearance from your specimens. Microanalysis is another thing. If you remember, I mentioned about birefringence and seeing special colors under cross-polarized light modes in optical microscope. That gives us chemical information. But with electron microscopes, we can go even deeper and more detailed. We can get an elemental composition and compositional distribution of our microstructures thanks to the characteristic X-rays that are developed from your microstructure. So these are the advantages of electron microscopes over optical. But there are drawbacks, of course. Number one, you must operate under vacuum. That means sometimes it can be detrimental for your cement paste. Why? Because your cement paste can have certain amount of water inside. If you evaporate that, if you dry it all the way, you might get cracks. And depending on your research, this can be detrimental or this can be negligible. It just depends on what you're looking for. But understand that you are generally operating under vacuum. There are new developments, of course, there are new technologies or newer technologies where you can operate under relatively less vacuum. which is less detrimental for microstructures like cement paste, but still you need to operate under vacuum. Otherwise, your electrons cannot reach your specimens easily. They will bump into the water vapor molecules, and they will be like skirted away, and that's something we don't want. So drawback 2 is the specimens must be conductive. Again, if you are using very high vacuum, you are sending your electrons on top of your specimen, those electrons should eventually go somewhere. If they don't, if they accumulate, then the next coming electrons will not be able to reach the specimen surface and they will be deflected, right? Minus rejects the minus. So this is a problem, of course. That's the reason we are using coatings like carbon coatings or gold coatings, depending again on your application, in order to let the electrons dive into our specimen, do its job, and go away. Okay. Again, if you use relatively less vacuum or water vapor, you can prefer not coating your samples, not making your samples conductive. But again, then you are losing some other features, like you will get maybe you will lose the possibility of doing full quantitative microanalysis. So again, just to summarize, I mean, there are advantages and disadvantages. So you need to know what you're dealing with, what kind of specimen you have, and what are you really looking for. Let's compare light and electron microscope. You see on the left-hand side, this funny picture upside down. Actually, this is the situation. This is just to make it compatible with the electron microscope, because you see my electron source is all the way on the top, but for optical microscopes, normally it's at the bottom. But just to give you an idea, I made it upside down like this. So now my light source is also on the top, okay? So it goes down through some series of condenser lenses, otherwise my light will be dispersed everywhere. I don't want it. I want to condense them on top of my specimen, which is right here. And in the electron microscope, it is all the way down on my stage. So my electron goes through a series of lenses and then finally focused on a spot. While in a transmitted light electron microscope, optical microscope, you have the source of light, goes through your condenser lens, goes through your specimen, your thin section, you remember, through your objectives and comes to your eye. Okay, I mean, it's give or take similar. And if you want to calculate the resolution, you need to use the wavelength in your emission and the numerical apertures typically you use, and then you will see the resolution in these two systems are way, way different. So let's look at the anatomy of an electron microscope. Again, electron source it's generated right here, goes through these lenses. These are magnetic lenses, not optical lenses, and goes through an aperture and falls on top of my specimen. The electrons enter the specimen, hits other atoms, do its job, we will talk about what it is, and then generates secondary electrons. So some new electrons will come out, and it's our wish actually to detect those electrons by using these detectors right here, so that we can convert the signal into image or chemical information, chemical compositional information. So what is this electron source we're talking about? Actually, it's just a light bulb. If we apply super high tension, you start increasing the heat, the temperature actually of this filament. And then at some point, which is 2700 Kelvin, electrons start to boil on this filament. And with a negative bias, you can pull them down and throw them on top of your sample. Okay. So this is a typical filament of a tungsten electron source. There are different sources. Maybe in your lab, you have different types. Maybe you have a relatively new system, field emission guns. We had, until recently, some tungsten filament type, but now we also have a field emission, a newer system, which we're very proud and happy about. So there are many advantages of those new systems. And the electron column, again, they are just made of series of lenses. You see, the whole idea is to keep the electrons on the trajectory and to be able to just let them fall on the specimen to the right spot. These scanning coils are very important because unlike optical microscope, you don't see everything in one go. It is the images are generated after certain rastering operations, scanning operations. So it is line by line, it is rastered and generated. That's the reason these scanning coils are doing a really, really important job. And when we talk about detectors, there are many detectors in electron microscopes, but I just want to talk about two of them today, which are the secondary electron detectors, which detect the low energy electrons from near surface. And there are the backscattered electron detectors, and they collect the relatively, sorry for the repetition, it's not low energy from near surface, it's copy-paste error. They are relatively higher in energy, and they are created from the, actually I can even change this right here. So they are, let's call this higher energy electrons from the bulk as well as the surface, bulk and surface. So this is, so these are two different electron types. And of course, that's the reason we can get different information from these two different electron types. What are they? For instance, if you can easily imagine that the secondary electrons, since they're coming from near surface, closer to the surface, they should give me information about the morphology, right? Morphology of whatever I'm analyzing. And backscatter electron is a little different. I hope I will be able to talk more about it here. You see, when I detect my secondary electrons, I get more topographical information, how it looks like, what's the shape of a crystal, and so on and so forth. And the backscattered electron gives me information about its mean atomic number. So suppose that you have here one phase, right? This is light gray. Here you have relatively darker gray, and you have here inclusions, and you see they are all in different shades of gray. And here you see super bright. So why are they all different? And the similar colored phases, are they the same phase? The answer is yes. All the light gray here phases are the gamma phases you're seeing. The relatively darker gray is the beta phase. And the reason we see them in different gray shades are because the average, the mean atomic number of this phase beta is lower compared to gamma. And gamma is again lower than the Ni5Y phase right here. Right here. All right. So on the one hand side, if I choose to operate to activate my BSE detector, suddenly I start getting information regarding my phase composition. And if I choose to use secondary electron detection, I get more topographical information. Again, this here you see you have some information about the image generation, the rastering operation I was talking about. And this is the depth of field. So on the left-hand side, you see the optical. So you see I have focused here. This is in focus, but the remaining portion is not in focus, you see. But if you look at here on the right-hand side, if I focus here, I can also focus the other parts. They're all in same focus. So the depth of field, the depth that keeps things in focus is really, really large in electron microscope compared to optical. Okay, so I was talking about the electron beam solid interactions because so far what we've talked about was the anatomy of an electron microscope, what it is, and how we generate the electrons and we send it on top of our specimen, but we didn't really talk about what's happening when the electrons come down and hit on top of our surface. And when it does, this is your primary electron beam coming down on your specimen. Again, they enter and they hit other atoms that are forming our specimen. Okay? And when this happens, of course, some events collisions happen, and as a result, you will get secondary electrons like this. You remember they were mainly coming from the surface because they are low in energy. Although we are generating them in the bulk, they will not have enough energy to escape and go to your detector. So that's the reason mainly we're getting information from the secondary electrons from the surface. Backscatter electrons, again, they are energetic enough. That's the reason they're coming from the surface as well as from the bulk. And there's one more thing, the characteristic X-ray. When our electrons come and hit a specific atom, let's say silicon atom, let's say calcium atom, when you hit that, you are generating an X-ray that is characteristic in energy and wavelength to that particular element. And then you can imagine that if your detector is hearing multiple times that particular X-ray, then it says, oh, I'm hearing a lot of signal from calcium. Let me plot them on a spectrum, and then I will get a calcium peak in my microanalysis result. It can be EDS or WDS, but again, I am not able to talk more about the X-ray part, but that is important so that we just put it aside and we just emphasize that it's important. There are other things like Auger electrons, which are coming really from the surface, super thin, but they are really, you need super special systems for Auger in order to be able to detect Auger electrons and cathodoluminescence. They need special detectors. In typical electron microscope, you will not be able to see these options. They are available, of course, but not very common. So this is what I'm talking about. If your main electron, the primary electron, comes and hits a silicon atom, and it will not hit any electrons, but it will just be backscattered to the surface, and then it releases there. This will have a high energy, and we call these kinds of electrons backscattered electron. If the primary electron comes and hits our first K shell right here, it hits my existing electron away and then creates here a vacancy, which means my electrons at the higher electron levels, higher orbitals, will start to replace the vacancy in a cascade fashion, which generates this characteristic X-ray. And our detectors can detect this and say, hey, I'm getting signal from the silicon element. And the others are, by the way, X-ray is here and the secondary electron is actually here, but I kind of gave the story for both only here. And Auger electron is something a little more detailed. I skipped this part. And the interaction is happening in this volume, actually, beam specimen interaction. So is this something fixed and you always have the same volume? No. As an operator, it's up to you to define at what speed, figuratively speaking, at what speed you are sending your electrons on top of your surface, okay? You can increase your accelerating voltage from, I don't know, 5 kilovolts to 10 to even up to 30 in typical systems. And the higher the accelerating voltage, the higher, the larger the interaction volume will be. Why is this important? Because you might be interested in the microanalysis of a super small area in your specimen. Let's say you generated some self-healing products, but they are really tiny. So if you choose to have very high accelerating voltage, you might think you're analyzing your tiny phase, but actually you are analyzing a huge volume because you chose unnecessarily high accelerating voltage. So you should be smart and try to lower your accelerating voltage so that your interaction volume will be small and you will get realistic information from your surface, from your spot analysis. Okay, so this interaction volume is really an important thing, and actually I'm observing people make a lot of mistakes by not paying attention to this accelerating voltage and interaction volume. You can easily model these and with some free software and make more sensible research. Please don't underestimate the importance of interaction volume. Again, here you see where the secondary electrons are generally coming from, and the backscattered electron is coming from this deep, and the characteristic X-rays are relatively deeper. So how deep is this? It can be starting from maybe half micrometer from, I mean, this distance and this distance, can be somewhere from half a micrometer going all the way up to 5 micrometers, depending on the specimen and depending on your accelerating voltage. Okay, these two things are so important. And again, you can model these with Monte Carlo simulations available on the internet. You can easily find freeware software to these to model beam specimen interaction. Okay, which is an example here. You see, if you model based on a, we assumed that it was an aluminum and 10 kilovolts accelerating voltage would generate electron trajects like this and X-ray generation from here. So if your specimen, your phase is so small right here, and you're interested in analyzing the chemical composition of this, forget about it at these settings because you're getting information from the neighboring phases, you see? So important. And these are for different materials and for different accelerating voltages. You see, you can change the interaction volume. Okay, some nice stuff. It's been quite boring. Let's appreciate the aesthetics of these images. You see, these are all secondary electron images. They give you very nice morphological information. You see the quartz crystal shapes. You can easily see all these beautiful euhedral crystals, so real shaped crystals. Beautiful. But these are indeed beautiful, and I also really enjoy looking at them, but you should really ask yourself if this is a useful technique, secondary electron imaging. It can be very interesting and useful at times, but don't forget, this technique is not quantitative, really. This is generally a qualitative or semi-quantitative, maybe. Why? Because the only thing we are seeing is a crack, perhaps, and inside a crack or cavity, you see some crystals, fine. But how much? I mean, is it only here or is it everywhere? Is it well dispersed, well distributed? So from quantity point of view, you have no idea. So that's the reason I really advise you guys, everyone, to concentrate on the BSC imaging as much as possible because it gives you 2D compositional images so that you can do image analysis, perhaps to do a compositional analysis. Then you can say I have 50% of phase gamma and I don't know 25% of phase beta and so on and so forth. Some stereological analysis you can do. That's the reason it's quite. I think it's far more useful for us to do BSC imaging and analysis if we want quantitative information. Speaking of backscatter coefficient, again, as I told you before, it is all about the mean atomic number. So the higher the mean atomic number, the brighter the phase, the lower the mean atomic number, the darker the phase. And this is quite advantageous for us, for concrete people or people who are dealing with porous materials. Why? Because those pores we are impregnating with we're impregnating with the epoxy, right? And that epoxy has a super low mean atomic number. So what's the advantage then? Of course, then we will see all our pores very dark compared to the rest. And that helps us to isolate the porous part and calculate our porosity, for instance, when we do image analysis. You see here also the backscatter coefficient. As we increase the mean atomic number of our phase, we see the backscatter coefficient increases, which means there will be then the higher grayscale. The brightness of the grayscale will be higher. It will be closer to white. And for different materials or different systems, you can do this, but you see for concrete, for instance, here on the left-hand side, you see important phases, and based on their mean atomic number, you can calculate the the backscattered coefficient, which can be translated into the relative measured image intensity. You see, this is the darkest and this is the brightest. So if you're looking at an image, a cement paste, then you will see, for instance, ferrite, A-light, B-light, calcium aluminate phases as relatively brighter compared to your epoxy or silica gel, right? They will be relatively darker because their backscattered coefficient is lower. Why? Because their mean atomic number is lower, relatively speaking. So let's look at how we're observing our cement paste. So this is a typical concrete microstructure. It's very low magnification. So look at the advantage of backscattered imaging. We have filled in our cracks with epoxy. That's the reason they are very dark. That's the reason I can easily say these are all epoxies. That's the reason they are cracks. I see here and there some pores, here and there, some capillary pores and so on, but I can know more about it even. I see here bright particles. You remember our table here? All the unhydrated cement grains are really high in backscattered coefficient. That's the reason you see these are all my unhydrated cement grains. And the rest, these grains are all my aggregates. So let's zoom in a little bit to know more. You see, I can easily zoom in. Unlike optical microscope, I can zoom in at really smaller steps. In optical microscope, whatever objective you have, you're limited to that. But with this one, you can really go very slowly. You can go down to observe this very single grain of Portland cement. So this is my unhydrated cement grain, and now suddenly I can see individual capillary pores. You see, with optical microscope, this wasn't possible. It was impossible. I could see the total intensity because of the amount of capillary pores, but with electron microscope, you can easily see even the very details of it, which helps us to take this photo, go to our image processing software, and calculate the amount of pores, for instance, or any other phases. You see, we can really see super details. Even I can see the ferrite phases and C3A phases easily. These are, I think, periclase, magnesium oxide, and so on and so forth. So I can take a picture. I can segment certain phases based on their grayscale, and then I can do image analysis. Very easy. Of course, concrete is not the only thing you can imagine. You can examine with electron microscopes. There are several different application fields, from wood, timber to biology science. The principles are just same. There is simply no difference between for different materials. The principle, once you know the principles, the rest is just knowing what kind of material you're dealing with and just analyzing it. Here is a little more relevant stuff for us. Self-healing of a crack. You can kind of guesstimate that the crack starts somewhere here, going all the way up to here, and everything in between is the calcium carbonate self-healing product generation. This is an image from one of our students, Emanuela. Here, this is of course a beautiful self-healing success, but this is just at a given moment. Here, another look at the healing. So you can clearly see that these are the products. They are all calcium carbonate, these grains. And starting from somewhere here on, you have the bulk. All right. So finally, I'd like to this is for your, of course, for your reference, not to teach you anything right now, but all I'm trying to say is that there are really many parameters if you're interested in doing good research with electron microscope. If you want to acquire quality images, sharp images, and do quality microanalysis, all these things need careful setting and good understanding of all these parameters. This is just these are just the important ones, not all of them, but still by taking these parameters into consideration, you can definitely have good control of your analysis. Do I have anything more? Yeah, some acknowledgements from friends, and hopefully you're not asleep. It's been quite some talking. Let me go back to your faces. Yeah, this is a good album, by the way. I mean, if you like listening to new stuff. All right, so this is, I mean, super crash course in microscopy general. I hope I gave you some ideas if you didn't know much about it. If you knew already, of course, this was a repetition. Sorry about it. But I think this was the only way I could give in 2 hours kind of every important topic on microscopy. So it's your turn. Any questions? Anything you would like to say? I don't know. Shoot.
Yeah, I have one question.
Yes.
Regarding the energy applied to BSA, how can we do the simulation in case of concrete that has several elements involved because it is a composite, not a specific element?
The best you can do actually is to do approximation. I mean, you will, of course, it will be difficult to know exactly what you have, but you can have a kind of estimation. How do you do that? Typically, first, you could do a very rough analysis on your specimen. Okay, if you do rough analysis, just forget about the accelerating voltage and even the specimen preparation or whatever. If you just analyze your interested surfaces, then you will get an approximate composition, right? It will not be super accurate, but you will get something. And that can help you to understand, hey, I'm looking at calcium-rich zone here. It appears like it's rich in calcium carbonate, or maybe, I don't know, it just depends on the composition you're getting. You can have good estimation. And believe me, if you have, if you understand it approximately, that is more than enough. You don't have to really know exactly what composition you have before you choose your accelerating voltage. All right?
Okay.
So that's, if you know approximately, that is totally okay.
Thank you.
Any more?
Yes, okay.
Sure. Sorry, I can't see your names, so I can't address you with your name. But go ahead.
In electron microscopy, when an electron hits an atom, so maybe an inner electron excited and go to the some higher energy, but not exit the atom, and then it has an opportunity to come back to the inner energy. So does it give us some information, or does it have some?
What you're defining is, of course, happening, but statistically speaking, the first K-shell interaction is happening far more than the others. And that's the reason we are getting that characteristic X-ray. I mean, there are really tons of interactions going on, but the one we are detecting is, statistically speaking, the event that is happening more. That's the reason we are observing that. But at the same time, Auger events are also happening, but we just can't detect it. It's just released, but I don't have a detector for that, so it disappears.
And it has no interruption with our others?
Probably it has, but I think it's negligible. You don't have to worry about it.
Thank you.
Any more? I think we have, like, how much time do we have?
Half an hour, but maybe it's good that actually it's 15 minutes, so that they have 15 minutes break before the next lecture.
Okay. So you said actually, Melodina, you were saying actually it's good that we do something.
It's good that we stop at 3:45, because then they would have a break before the next lecture. Next lecture is at 4.
Totally. That's the reason. I mean, this is, I think, good amount of time
for discussion. Yes.
Yeah, your questions if you have, especially if you have a question about the microanalysis part, which I really couldn't cover. I can.
Oguzhan, I don't know about the others, but I cannot hear you now.
We can hear.
Can you?
Yeah, it's.
But maybe it's only me.
Yeah.
Can the others hear him?
Yes.
Yeah. Yes.
Okay. I think that the others hear you.
Oh. I think she has to pay more.
Strange.
Okay, questions?
Oh, now I hear you.
Excellent. Yeah. No question. Nobody's interested in microscopy.
I have another question. But is regarding to the preparation of the sample, because when we have a crack, I don't know, I never work with this, but I imagine that it's difficult to cut the sample with the crack without disturb the self-healing products inside.
Yeah, certainly. I mean, if you're interested in analyzing formations in a crack, of course, the first thing you should do is to impregnate your surface, your sample. It is extremely important. So what do I mean by that? You put your sample in a vacuum environment, you take all the air out, and then you send your epoxy in while all the air is out, because then there will be no air to kind of obstruct the penetration of epoxy. So epoxy will penetrate in the cavities of your sample, and then you release the air back so that it will push the epoxy to every single detail of your porosity, and then you take it out and let it cure. So next day, your specimen will have enough kind of resistance to withstand the effects of cutting. I mean, you will cut, but your crack will stay there. Everything inside will be attached to the epoxy, so there will be no problem.
But there are a limit to this sample that you impregnate, because sometimes we work with big samples and.
Of course, I mean, if we're just talking about, perhaps I will just make it up, but just from my experience, several hundred micrometers tops you can impregnate. So if it's a really thick sample and you're interested in cutting the middle part or examining the middle part, it doesn't make sense that you impregnate from outside and you cut and look and see the crack. That is not possible. If you want to do that, one option could be to cut your sample not at the surface you're interested in, but a little bit thicker, impregnate, and then try to grind it down. That could be one option.
Okay, thank you.
Your thickness and penetration is, of course, actually the capillary porosity, amount of capillary porosity is directly related to amount of epoxy it will accept, right? So it depends on your specimen. Is it cracked? Is it non-cracked? Is it porous? Is it not porous? Is it permeable? Is it not?
Thank you.
Any more?
Oguzhan, if there are no more questions, there are also some questions in the chat here from the.
How do I see that?
From the attendees. Here in the right corner, you see this question mark. So from the left.
Find the. I think I should go to the Teams, right? I should go to SmartThings, and there should be somewhere the chat option.
No, it's in the same window. So it's in the same window. It's you see first is the line with the.
Yeah,
and
I saw it.
The second one with a question mark.
The anonymous is asking the darker the lighter, I think. Is that the
yes.
one? Or?
So let's see. I think your part starts from carbonation. I think this was the answer on one of your questions, and then there is UV light.
Oh yeah, there you go. Should I check the published ones?
Yes.
Okay. All right. So which one? Ladena, thank you. You're welcome. I think, yeah, UV images. I think I should start there.
Yes, exactly. UV
All
images.
Right. UV light images that you showed in the last slide were thin sections. I think so, but I don't know. Let's go quickly check.
Because there is also one of the students asking if you would have this presentation available, and I think yes. Because we also published the SmartThings. Yeah.
I think it would be evil not to. Yeah, I mean, if you're asking, because the last one was about water cement ratio, capillary porosity relationship. Yes, indeed, that was the thin section image. Louise asks, can visualize the zeolite formation in geopolymers under XPL filtered images? It might be very unlikely because zeolite grains are super, super small. I would more use the electron microscopes for that, but zeolites, you can see the effect of using zeolite, of course, with XPL or fluorescent light intensity, fluorescent light microscopy, but observing them individually, I think it will be super difficult because of the resolution. Which techniques are used to stop hydration on early age so you can study microstructure on that moment? Typically, there are a couple of methods people use. Isopropanol is one method. Some people use acetone with mixed feelings. Some people say the morphology is changed when you use acetone. And then another option would be to immerse your sample in liquid nitrogen to stop hydration and then to put in a desiccator. So these are typically what people use. I think isopropanol soaking is the most commonly used technique these days. Kind of people agreed upon this. Another question talks about which techniques are used. That's we read because we are not using visible light. Oh, there were answers to my questions. I'm so sorry I didn't see in the chat window, but you get the cookie points, no problem. Can we please get the slide? Yes, you will of course get. And the darker phases in BSE is also related with crystal packing. The darker, the heavier or denser. I don't know what you exactly mean, but crystal. Oh, no. Now I understand. You're talking about, for instance, body-centered cubic, face-centered cubic type of atomic packing density. No, it has nothing to do with that density. It is directly related to mean atomic number. That's it. What I'm trying to say is this. Imagine two different, one BCC and one FCC metal, having only single element, okay? Then your backscattered electron coefficient would be same because the mean atomic number is the same because you don't have any other elements. It's a single element. So it has nothing to do with the crystal packing. It is the mean atomic number. That was the last question.
Yeah. Then I would say if there are no more questions, thank you very much, Oguzhan.
Sure, it was a pleasure.
A great presentation. And then I would suggest that we make a bit longer break, 5 minutes longer break, because otherwise we're also tired.
You're also welcome for that. Excellent. It's always nice to see interested people to microscopy. Very nice. And maybe I will see some of you later on during your projects. Excellent. Okay, then I think it's time to say goodbye.
Bye and thanks.
Bye, thank you.
Bye.
Thank you.
Goodbye.
Thank you.
I will upload the slides. First, I need to convert to PDF and then I will upload.
Yes. Okay. Thank you.
Take care. Bye-bye.
You as well.
Bye.